In 2015, humanity heard the universe scream. Two black holes had collided, but one question remains unanswered. A question that could shatter everything we thought we knew about the stars. Where do the biggest black holes come from? And what if the answer breaks the laws of stellar death? For decades, astrophysicists lived by a simple rule. A star lives, a star dies. If it's massive enough, it collapses into a black hole. That was the story. Clean, predictable, almost comforting. But then came the anomalies. Black holes too heavy to have been born from a single dying star. Too heavy and spinning wrong. Something else is out there. Something ancient, violent, and deeply hidden. To find it, we have to listen not with our ears, but with the bones of space-time itself. September 14th, 2015, 5:51 a.m. Eastern Time. In Livingston, Louisiana, a laser beam inside a 4-kilometer-long vacuum tube trembles. 1,800 miles away in Hanford, Washington, the exact same tremor. 7 milliseconds later, it wasn't an earthquake. It wasn't a truck. It was a gravitational wave. Predicted by Einstein in 1915. Detected a century later. The sound of two black holes merging 1.3 billion light-years away. That signal was named GW150914. And it changed everything. Because the black holes that created it were bigger than theory allowed. Not a little bigger. Masses of 36 and 29 times that of our Sun merging into a 62 solar mass giant. Stellar evolution models blinked in confusion. How do you get a 36 solar mass black hole from a star without the star blowing itself apart first? Stars are not gentle exiters. When a very massive star ends, it doesn't just fade away. It explodes. A supernova so violent it can outshine an entire galaxy. But there's a catch. If the star is too massive, above 100 times the Sun's mass, something strange happens. Inside its core, gamma rays become so energetic they turn into pairs of electrons and positrons. This pair-instability process collapses the star's core prematurely. The explosion is total. No black hole left behind. That's the pair-instability mass gap. A celestial graveyard where black holes cannot be born from a single star. Theory places that gap between roughly 45 and 130 solar masses. But LIGO, Virgo, and KAGRA kept finding black holes inside that gap. Not above it. Inside it, where they should not exist. So either the models are wrong, or these black holes were made another way. Enter the globular clusters. Imagine a sphere of stars packed millions of times denser than our Sun's neighborhood. In these crowded stellar slums, gravity runs wild. Stars don't just orbit, they collide. And where stars collide, black holes can merge. Repeatedly. This is the hierarchical merger theory. Small black holes combine into medium ones. Medium ones combine into large ones. Each merger kicks the resulting black hole, changing its spin and direction. Over millions of years, these dense clusters become factories of monsters. But proof was missing until the spins spoke. Dr. Fabio Antonini at Cardiff University led a team. They analyzed 153 black hole mergers from the GWTC for catalog. They didn't just look at mass. They looked at spin. Lower mass black holes, those below 45 solar masses, spin slowly. Their spins align neatly with their orbital planes. That's the signature of black holes born directly from collapsing stars. Quiet, ordered, but above 45 solar masses? Chaos. Higher mass black holes spin faster, and their spin axes point in random directions, misaligned with their orbits. That is the fingerprint of past mergers. Violent, repeated, hierarchical, as Dr. Isobel Romero-Shaw put it. This is the exact signature you would expect if black holes were repeatedly merging in dense star clusters. For the first time, the mass gap wasn't a contradiction. It was a clue. The universe, it turns out, builds black holes in two very different ways. Population 1. Single star collapse. Clean, predictable, forms black holes up to about 45 solar masses. Population 2. Hierarchical cluster mergers. Chaotic, ancient, forms black holes that pierce through the mass gap, reaching 50, 80, even 100 solar masses. The transition is sharp. At 45 solar masses, the spin distribution flips like a switch. That's not an accident. That's a wall. On one side, stellar graveyards. On the other, cluster battlefields. Antonini's team found that the heaviest black holes in the current sample aren't telling us about stellar evolution alone. They're telling us about cluster dynamics, about star clusters so dense that black holes hunt each other down over eons. But here's the deeper question. If massive stars don't collapse directly into heavy black holes, then every black hole above 45 solar masses must have been assembled, piece by piece, collision by collision. That means the biggest black holes are not first-generation objects. They are second-generation, or third, or 10th. They are fossils of a hidden history. A history written not in light, but in gravity. And that history forces a choice. Either our models of stellar evolution are wrong, and some massive stars do collapse directly into heavy black holes, or the models are right, and the mass gap is real, which means every heavy black hole we've detected was forged in chaos. Dr. Antonini puts it bluntly. The key question now is, are these black holes telling us that our models of stellar evolution are wrong, or are they being made in another way? The answer is coming, but not from telescopes, from interferometers. LIGO is upgrading to A+ sensitivity. Virgo is expanding. KAGRA is cooling its mirrors to quantum limits. And next-generation detectors like the Einstein telescope and Cosmic Explorer will see deeper into the universe's gravitational wave background. They won't just hear mergers. They'll hear the ring up, the ring down, the precession of misaligned spins. They'll tell us not just that black holes merged, but in what kind of environment, and how many times before. Every new detection adds a line to the obituary of a star, or to the biography of a cluster. And somewhere out there, right now, two black holes are spiraling toward each other. Their final dance has already begun. Millions of years ago, the ripple is already crossing the void. We are the first generation of living beings to hear the universe in gravity. Not through light, not through sound, through the stretching and squeezing of reality itself. Every black hole merger is a message. Every spin misalignment is a confession. The biggest black holes aren't just dead stars. They are recycled killers, assembled in the densest nurseries in existence. So the next time you look up at a clear night sky, remember, the darkest points aren't empty. They're listening. And if you listen carefully, so are we. Subscribe. Stay curious. The universe is still writing its story.